Hello students, let us discuss one more example based on Congruence Modulo 3. Question is, show that Congruence Modulo 3 is an equivalence relation on Z and find the equivalence class containing 0, containing 1, containing 2. Also find the partition on Z. That is, we have to show that this Congruence Modulo 3 is an equivalence relation and we have to find out the equivalence classes containing 0, equivalence class containing 1, equivalence class containing 2 and also find the partition of Z. We already know the definition of partition of Z and some example based on partition. First we have to prove that the congruence modulo 3 is an equivalence relation on Z. Already we have proved that congruence modulo n is an equivalence relation. Just replacing n by 3 we will get the same result, or we will prove this congruence modulo 3 relation is equivalence relation. So first we have to prove that this relation is a reflexive relation. For that, let A belongs to Z. We have 3 divides 0 because this 0 can be written as a multiple of 3. So 0 is equal to A minus A. So 3 divides A minus A, that is A minus A is congruent to A modulo 3. So and this holds for all A belongs to Z. Therefore this congruence modulo 3 is a reflexive. Symmetricity, let A comma B belongs to Z. Suppose A is congruent to B modulo 3, we have to prove that this B is congruent to A modulo 3. If A is congruent to B modulo 3, then 3 divides A minus B by definition of congruence modulo 3. This implies that 3 divides minus of this A minus B, so minus of A minus B. This implies that 3 divides B minus A, so B is congruent to A modulo 3. So this congruence modulo 3 is a symmetry. Now we are going to check whether this congruence modulo 3 is transitive or not. For that, let A comma B comma C belongs to Z be any 3 elements. Suppose A is congruent to B modulo 3 and B is congruent to C modulo 3. So by definition of congruence modulo 3, this implies 3 divides A minus B and 3 divides B minus C. This implies that 3 divides A minus B plus B minus C. Why? Because we have already proved that if A divides B and A divides C, then A divides AX plus BY for any X and Y. So this 3 must divide addition of these two integers. So 3 divides A minus B plus B minus C. So B get cancels with this minus B. So 3 divides A minus C. This implies that A is congruent to B modulo 3. Thus congruence modulo 3 is a transitive. From 1, 2 and 3, this congruence modulo 3 is an equivalence relation. Just replacing n by 3, you will get the same thing, that is congruence modulo 3 is an equivalence relation. Now we are going to find out the equivalence class. Already we have seen the concept of equivalence class. We have to find the equivalence classes. First we have to find the equivalence class containing 0. So what is the definition of a equivalence class? Equivalence class containing A is denoted by square bracket A, and this is nothing but the all B belongs to Z or set X or A such that B's are related to A. So elements related to A are comes in the equivalence class of A. Therefore equivalence class containing arithmetic. So elements in the equivalence class of 0 are nothing but the which are related to 0 by the relation congruence modulo 3. So this is nothing but the all elements X belongs to capital Z such that this X is congruent to 0 modulo. So equivalence class of containing 0 is nothing but the all elements X belongs to Z which are related to X. Here the relation is congruence modulo 3. So X is related to 0 means what? This X is congruent to 0 modulo 3. So this is equal to all X belongs to Z such that 3 divides X is congruent to 0 modulo 3 means what? 3 divides X minus 0. So this is equal to X belongs to Z such that 3 divides X minus 0 means 3 divides X. This is equal to all X belongs to Z such that 3 divides X means what? X is a multiple of 3. So X equal to 3K and this K belongs to z. So this is nothing but the, now x is 3k such that k belongs to z. So when you put the some values of k here, so you will get, so for k equal to minus 3 you will get minus 9, k equal to minus 2 you will get minus 6, all the multiples of 3 minus 6, k equal to minus 2, k equal to, you will get minus 6, k equal to minus 1 you will get minus 3, k equal to 0 you will get 0, k equal to 1 you will get 3, 6, 9 and so on. This is the equivalence class containing 0. Let us find the equivalence class containing 1. Let us find the equivalence class containing 1. This is nothing but the all x belongs to z, this such that this x is related to 1. So this x is r related to 1. For your understanding I have written this. Here r is equivalence class, equivalence relation, congruence modulo 3. So x belongs to z such that x is congruent to 1 modulo 3. So this can be written as all x belongs to z such that 3 divides x minus 1. So x is congruent to 1 modulo 3 means what? This 3 divides x minus 1. So this is equal to all x belongs to z such that 3 divides x minus 1 means what? X minus 1 is a multiple of 3, 3k for some k belongs to z. So this is nothing but the, now our x is, all x belongs to z such that x is equal to 1 plus 3k, k belongs to z. So this is equal to, now x is 1 plus 3k and k belongs to z. So this is equal to, how you can write this? This is equal to 1 plus 3k such that k belongs to z. Z is a set of integers here. So this is equal to, see here, this is a set. For k is equal to minus 3 we have minus 9 plus 1 is minus 8. For k equal to minus 2 we have minus 6 plus 1 is minus 5. K equal to minus 1 we have minus 2. K equal to 0 we have 1. K equal to 1 we have 4. K equal to 2, 6 plus 1 is 7. Then 10, because 3 into 3, 9 plus 1 is 10 and so on. So this contains elements of this form 1 plus 3k. Now we are going to find the equivalence class containing 2. This is equal to all x belongs to z such that x is r related to 2. So this is equal to all x belongs to z, capital Z, such that x is congruent to 2 modulo 3. So this is equal to, because our relation is modulo 3, this is equal to x belongs to capital Z such that 3 divides x minus 2. So this is equal to all x belongs to z. 3 divides x minus 2 is, means x minus 2 is a multiple of 3. So x minus 2 can be written as 3k, k belongs to z. So this is equal to, see here x is equal to 2 plus 3k. So this is 2 plus 3k such that k belongs to z. So this is nothing but, put some values. For k equal to minus 4 you will have minus 12 plus 2 is minus 10. So minus 10. For k equal to minus 3, minus 9 plus 2 is minus 7. For k equal to minus 2, minus 6 plus 2 is minus 4. K equal to minus 1, we will have minus 1. For k equal to 0, we will have 2. For k equal to 1, we will have 5. K equal to 2, we have 8. K equal to 3, we have 11 and so on. This is the set containing elements of the form 2 plus 3k. Now see here, these equivalence classes, the equivalence class containing 0 contains all the elements of the form 3k such that k belongs to Z. Equivalence class containing 1 have all the elements of the form 3k plus 1 such that k belongs to Z, and equivalence class containing 2 has all the elements 3k plus 2 such that k belongs to Z. So this is nothing but this is, and so on, minus 9, minus 6, minus 3, 0, 3, 6, 9 and so on. Okay, so these elements are nothing but, and so on. So here 3k plus 1, this is minus 8, minus 5, minus 2, 1, 4, 7, 10 and so on. Okay, so these elements are of the form 3k plus 2. So this set has the element minus 7, minus 4. Why we will get minus 4 here? For k equal to minus 2, minus 6 plus 2 is minus 4. So minus 7, minus 4, minus 1 for k equal to minus 1, 2, 5, 8, 11 and so on. So see here, these all equivalence classes are mutually disjoint. So equivalence class containing 0, intersection equivalence class containing 1, is there any common in these two? In these two, is there any common in these two? Nothing is common, so their intersection is 5. Similarly, equivalence class containing 0 and equivalence class containing 2 is 5. Similarly, equivalence class containing 1 and equivalence class containing 2 is 5, because there is no elements in common. Also we have these equivalence classes are, see here, this equivalence class containing 0, this is a subset of Z, proper subset of Z. Again this is a proper subset of Z. All these elements are the elements of Z. So these are the subsets of Z. And see here, when you take the union of all these three things, equivalence class containing 0, equivalence class containing 1, equivalence class containing 2, so what you will get? See here, Z contains 1, 2, 3 and so on, 0, minus 1, minus 2, minus 3 and so on. So 0 is here, 1 is here, 2 is here, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So for minus, 0 is here, minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7, minus 8, minus 9 and so on, minus 7, minus 8, minus 9. Again minus 10, where will you get minus 10? For k equal to 4, minus 4, minus 12 plus 2 is minus 10. Here minus 10 we will have minus 10, minus 11, minus 12. In this way, this union of all these three equivalence classes gives us the whole set Z, the set of all integers set. So these partitions 0, 1 and 2, these equivalence classes are mutually disjoint. These are subsets of Z and whose union is Z. Therefore this P, all these three equivalence classes gives the partition of a Z. So the P is equal to equivalence class containing 0, equivalence class containing 1, equivalence class containing 2 is a partition of Z, is a partition of Z, partition of Z. So if we want to calculate equivalence class of 3, so is 3 is here in this equivalence class 0. So equivalence class of 3, you will get, you calculate equivalence class of 3, you will get equivalence class of 3 equal to equivalence class of 0. So this is the partition of inside. Hope you will understand. Thank you, students.